For many functions, especially functions that describe the real world, only certain x values are allowed, and those are called the domain of the function. And we're going to look at several different examples of different restrictions on the domain. Let's first look at a function definition. For instance, here's a function that describes the profit you can get based on the price you have for a product. So P, large P here, is profit. It's a function of price, which is x, and it equals 40x minus 0.2x squared. Now, because this is a price, we know that we don't want to have a negative price, so the domain is x is greater than 0. So your price has to be greater than 0. That only makes sense. So what we see here is here's a real-world situation where in the function definition, right here, written right here with the function, we see that there's a restriction on the domain. X has to be positive. And a lot of times you'll see a restriction there. You won't always know why there's a restriction, but a function might have a restriction. If it doesn't show a restriction, then the function's domain is all the real numbers. Remember sequences? Well, with a sequence, the domain is usually the positive integers. Why is that? Well, a sequence is inputs are 1, 2, 3, 4, 5, the first, the second, the third terms of the sequence. Now, sometimes a sequence will have the first term be 0, in which case you might have the non-negative integers be the domain of the function. Let's look at a couple of graphs. In the first graph here, we have a linear equation is graphed. There's a line. And we only see a part of the line because it goes on forever in both directions. And there's no indication that it's going to do anything but go on forever. So the domain, the x values, will be all the real numbers because it will continue for any x input to the right or to the left of this graph, we're still going to get a result, an output for y. Now this right-hand graph is a little bit different. We see that it seems that the line goes on forever to the right, but we can see that it stops here at the y-axis. And it looks like it actually touches the y-axis. So for this graph, it looks like the domain is x is greater than 0, kind of like the function that we had up here. So oftentimes you can tell what the domain is, or you can make some assumptions about what the domain is just by looking at the domain's graph. Sometimes there will be a restriction on the domain of a function based on the function itself. For instance, here we see that x cannot equal negative 2. Why would that be for this function? Well, if x did equal negative 2, then we would have negative 2 plus 2. This would be 0 in the denominator of a fraction. We'd be dividing by 0, and that's undefined. So this function calls out the fact that x should not equal negative 2. So, what should the domain of this function be? Well, it should be all the real numbers except the ones that would make this fraction division by 0 or this fraction division by 0. What numbers would those be? Well, we can't have 0 itself, so x is not equal to 0. And we can't have x equal to 1. So x is not equal to 1. So here we have a function where we're just calling out two numbers that x cannot equal. So basically, we've looked at a number of different reasons why the domain of a function would be defined, and we've looked at how it's defined. One other term that you should probably be familiar with is range. Range is just the values that y will have for a function. So if you put in all of the different values that are allowed for x in any of these situations, then what are the possible values you can get for y? And that's the range. The most important thing to remember, though, is really the domain, and that you can't put any x values as inputs into the function unless they're part of the domain. Otherwise, the function doesn't remain true.